Hello everyone, welcome to the Material Science class MIC 300. This is the second video of the comprehensive discussion that we started over the previous video, that we are interested in investigating some important cases of the material and understanding what are the changes over the material microstructure and mechanical properties depending on the material processing. We discussed over the previous video the strengthening mechanism for pure material or alloy material that would be, or metals that would be processed by severe plastic deformation at room temperature, for example, or whatever, that it will be combined with some like core drilling operation. Even it could be combined or followed by annealing process. So these are the things that we covered over the previous video, and today we're going to continue the same topic with giving more comprehensive discussion about these cases and how again the microstructure, the mechanical properties would be related to the material processing. Alright, so in example 3, we're gonna focus over the mechanical properties and the microstructure of nanocrystalline material. So all the previous example, we were discussing that a conventional material like pure metal, that it will be plastically deformed, or we could do alloying to this material, and we explain the microstructural changes or the changes over the material microstructure and mechanical properties. But how about if we do have a material that is a nanocrystalline material? As we defined the nanocrystalline material, this is a material with nanograins. We said that the conventional form of the material, that it comes with grain, and the grain size, it is typically like around 20 micrometer, the average grain size 30 micrometer, 40, 50, 100 micrometer, or even less, but anyway it is in the micro scale. So that's why we are giving it a name as a material with microstructure. This is the conventional form of a polycrystalline material that has multiple grains, and the average size of these grains is gonna be like around in the micro scale. But we said that up on the plastic deformation of the material, we could decrease the grain size, and it could decrease to like hundreds of nanometer. Or it's gonna be like around 500 nanometer, 300, 200, 100 nanometer, around that case. If we can perform the plastic deformation over the material severely to decrease the grain size into a few nanometers or tens of nanometer, like 10 nanometer, 20, 30, 50, lower than 100 nanometer, in that case we are going to end up with a nanocrystalline material. So the material, in case that the grain size, it is around like hundreds of nanometer, we're gonna give it a name as ultra fine grain material. Ultra fine grained material. This is the material with a grain size that has been decreased because of a severe plastic deformation of the material into hundreds of nanometer scale. But if we can decrease the grain further to a few nanometers, like as I said, 10, 20, tens of nanometer, in that case we can give a name to this material as a nanocrystalline material. And we define the nanocrystalline material as a material with nanograins. So think of it, assume that we do have a material that is a nanocrystalline material, and this schematic, this figure, I've brought this figure from one of my paper. I presented this figure as a representation of the atomic structure and the microstructure of a nanocrystalline material. So think of it like the size of all of these different grains are in nanoscale. So this like 10 nanometer, 20 nanometer, 30 nanometer, around that range for all of these grains. So these green circles indicate the atoms that located inside the core of every one of these single grains. And these other blue atoms that located over the surface, this represent the surface, the exterior of any grain. Any solid object, anyway, it should have a surface. It should have a bulk, this bulk or core, which is the interior of this solid object, and there should be a surface. So this grain has surface, and I just to distinguish the atom that located over the surface of every single grain, I give them blue colors. Make sense? So these green grains, atoms represent the atom that located inside within the core of the grain, and the blue atom represent the atom that are distributed over the surface that form the surface of this grain. The same thing for all the grains. These dark or black atoms represent the atoms that receding in the grain boundary. We said that there should be grains, and these grains will have multiple crystallographic direction. There should be grain boundary between them. So this white background and with these dots, black atoms, these represent the atomic structure of the grain boundary. So these represent the grain boundary that exists in that case. So this is, as I mentioned, I have generated this figure that represent all the possible defects that we would experience or observe, except like many of them, I didn't include the dislocation here. But anyway, this figure represents so many of the imperfections that would be exist inside the crystal the material structure of a nanocrystalline material. And this figure was it was represented in one of my studies that about the effect of the processing condition on the microstructure and mechanical properties of Ecap titanium that published in Material Science and Technology. But anyway, so it means that most of the discussion that I'm going to represent here, it will be related from my research about the mechanics and the mechanical properties of nanocrystalline material. I can claim that I have made some good contributions in this field by developing some models and theories about the understanding how we can understand the mechanics of this nanocrystalline material and understand the correlation between the grain boundary of this material and their grain. So anyway, as I said, most of the discussion it will be extracted from or already from my research about the mechanics and mechanical properties of nanocrystalline material. But anyway, it is required here to explain all the microstructural imperfections. All the microstructural imperfections. We discussed in chapter 4 that we do have so many different types of crystal defects or microstructural defects, like the point defect, like line defect, interfacial defects. So we are going in the first part, it is required just to explain all of these microstructural defects that you can observe in this schematical representation of the microstructure of a nanocrystalline material that is shown in the film 4 of the material microstructure. So let us just focus over the first part and just mention and explain the different imperfections that we can observe. As we explained in chapter 4, we do have point defects. These point defects, it could be vacancies, it could be interstitial atoms or substitutional atoms. So can we see any one of these defects here within this microstructure of a nanocrystalline material? Yes, there are some of them. As you can see, if we're going to observe this grain, we said that these point defects are related to one missing atom or an extra atom. It means that it is related to one point within the crystal structure. So these point defects are located inside the grain. It should be located or identified inside the grain or the crystal structure. So these grains are crystals. So this is one crystal, another crystal, another crystal. Within this one, for example, I don't observe any missing atom or interstitial or substitutional atom. But for this one, for example, there is a missing atom here. There should be one atom located at this lattice site, so this could be considered as a vacancy. So this missing site, it is a vacancy. So we are expecting that we do have vacancies, and in case that it is multiple, so definitely this is one of the point defect that I can see here, and I can name this defect as a vacancy. So we can name this defect here, this one as vacancy. So we do have here vacancy. Okay. Another type of the defect is the interstitial or substitutional atom. Interstitial, as we defined it in chapter 4, it means that there should be some atom that already receding between the gaps, between the different lattice sites or between the different atoms of the host material. So, but the interstitial, I cannot observe a specific interstitial, but I can observe substitutional atom. Like this atom, it is substitutional atom. This is substitutional atom as one of the defects. As you can see, this is like an impurity inside the crystal structure, and somehow it replaces some of the atom. There should be one atom here of the green atom of the host material, but this dark blue atom, somehow it replaces the green atom that it should be located at this lattice site. So this is another form of the point defect, and in that case you are going to explain what does it mean substitutional atom, what does it mean vacancy atom, as explained already in chapter 4. So these are two defects which are qualified or classified as point defects. In addition to the point defect, we probably do have a line defect, and we said that this line defect is gonna be represented in the form of dislocations. And we said that we do have different types of dislocation. The one that we can observe easy over the material microstructure, especially from this atomic structure, is the edge dislocation. We defined that the edge dislocation in chapter 4, it should terminate. It is a plane of atom that terminates inside the crystal. It means that the irregularity in the crystal structure or the atomic distribution, it doesn't necessarily indicate a dislocation. The dislocation requires an extra plane that terminates inside the grain to be qualified as an edge dislocation. So if we're gonna try to observe any edge dislocation, probably we're gonna find there is no edge dislocation that we can observe from this representation, but simply I could include any dislocation. This could be one of the things that definitely could be exist in nanocrystalline material because of the severe plastic deformation. So for example, as you can see, this crystal or this grain, it is very perfect, right? There is no lattice distortions even within this grain, but there are some lattice distortion within this plane, but the main reason behind it is the substitutional atom. Here we would have some lattice distortion probably because of some vacancies or any other things, but we cannot observe a specific dislocation. The dislocation required, for example, like you're gonna have a row of atoms that terminates, and you're gonna have the dislocation line, it is somehow terminates at this point. So I can say that this is, in case that this thing is squeezed here, we're gonna say that this is a dislocation. But here you probably won't gonna find any specific grain that has a dislocation, but something that you should expect or consider that we should expect for this nanocrystalline material, there should be some dislocations that could be existed within these different grains. Make sense? So the line defect is one of them, but there is nothing observed within this representation of this figure. In this figure, I was focusing on other mechanisms than the dislocation, so that's why I didn't represent any dislocations here. But definitely, there should be some dislocation that could be generated within these grains, as we mentioned before. Make sense? The other defect is the interfacial defects. Interfacial defects, like for example, as we discussed, we defined the interfacial defect. This is the grain boundary. This is one of the common types of the interfacial defects. Also the surface. We discussed in chapter 4 the external surface. We said that any grain, it has an external surface. And here we are talking about the surface of the nanograin itself. So there should be some, this is another type or form of defect, and we are going to explain what is this defect. Anyway, we have explained this in chapter 4. What is the interfacial defect that comes from the external surface, whatever for the material or the external surface of a crystal or a grain. So for the grain boundary, as we said, these black atoms represent the atomic structure of the grain boundary. As you can see, it is very random atomic structure, and that's why it will be counted as a defect. And we said that this grain boundary in the conventional form of the material, if we're going to talk about the polycrystalline material that has multiple grains, every grain has its own crystallographic direction, orientation. And the difference in the orientations between two different grains, this will result in a virtual grain boundary. There should be like a grain boundary that is going to form here, right? So in the conventional form of the polycrystalline material, if you're going to compare the fraction or the part of the grain boundary inside the material microstructure in comparison to the grain itself, it is very negligible. The grain boundaries, they are very, very negligible in comparison to the grain themselves. The fraction, the percent of the grain boundaries inside the material microstructure, it is very negligible. So the question is, how about if we have a nanocrystalline material? This is for the polycrystalline material, the conventional polycrystalline material, the grain size is in the micro scale. So the grain is too huge in comparison to the grain. So the grain in comparison to the grain boundary. So that's why the grain boundary is very negligible. But in the nanocrystalline material, in a nanocrystalline material, we are decreasing the grain size severely to a few nanometers. So the grain boundary expands, extends, and becomes bigger. And in that case, the grain boundary is going to be a big deal for the nanocrystalline material, and it will be significantly affecting the mechanical properties of a nanocrystalline material. As you can see, if you're going to compare the size of the grain boundary to the size of the grain boundary, it is big. It could consume 50% of the material microstructure, it could be grain boundary. But in the conventional form of the polycrystalline material, in case that the grain size it is in micro scale, the fracture of the grain boundary, it is very small. It is less than even 0.1% of the material microstructure is going to be grain boundary. So in many of the cases, we just neglect the effect of the grain boundary on some of the mechanical properties of the material, like the elastic modulus, and we just consider this grain boundary as impedance for the dislocation to move, as we explained in chapter 7. But for a nanocrystalline material, since the grain size is too small, the grain boundary could take 50% of the material microstructure is going to be grain boundary. So it is a big deal, and it is one of the defects that would be found inside the material microstructure. Another defect as interfacial defect is the surface of the nanograin. Since this grain it is nano, and as we discussed in chapter 4, any grain or crystal, it will have an external surface. So the external surface here will be conjugated with an excess energy known as the surface energy, that for this atom that located over the boundary or the surface of this grain. So this grain has some surface atoms. These atoms will be underbonded, and this would result in some excess energy known as the surface energy, and this surface energy will impose some lattice distortion. That's why it is counted as a defect inside the material microstructure. In addition to the grains and these interfacial defects, we do have volumetric or volume defect. That defect that described over the volume scale as a volume. Like the pores, and this is the first time that we discuss this type of volumetric defect as a material defect. And it was not mentioned in chapter 4, but as you can see, these things are cavities, these are pores, voids, that found inside the material microstructure. So these are pores or cavities. This is also another defect inside the material microstructure, but it is volumetric defect. And since we are talking about nanocrystalline material, mostly these pores will be formed because of the severe plastic deformation of the material, and these voids inside the material microstructure will be in the form of as nanopores, nano voids inside the material microstructure. Since they are nano, the pore itself, it has a surface, because it should be surrounded with some atoms surrounding this void. Like all the atoms will be somehow distributed randomly or around the pore, and the thing in the middle, it should be void. So this is gonna give an internal surface. Do you see this? Just observe this, the atom that located over the direct surface of the pore. These atoms will have excess energy very similar to the excess energy for the atom that's surrounding the grain. So the atom that's surrounding the pore also, they do have excess energy, extra energy due to known as the surface energy, and is gonna be considered. It means that the pore, the existence of the pore inside, or the void inside the material microstructure of a nanocrystalline material, it will contribute to two different defects. One defect is being as a pore, as a volumetric defect. The second defect, that this pore itself, it has a surface, so it will produce some interfacial defects. So the pore has two defects, one interfacial, the other one is volumetric because being as a pore. Make sense? So this is for the first part. It's just to discuss and explain all the microstructural imperfection that we can observe within this material structure of a nanocrystalline material. Alright, so since we explained and identified these different imperfections that would be found inside the material microstructure of a nanocrystalline material, what is the influence or the effect of each one of these imperfections on the plastic deformation as a slip? We said that the observation of the plastic deformation through the material microstructure is known as a slip of which indicate the dislocation motion. So what is the influence of every one of these different imperfections, these point defects, the interfacial defects, the line defect, the volumetric defects, how they would impede or allow, what are their contribution to the dislocation motion inside the material microstructure or the generation of plastic deformation of the material. In the meanwhile, what are their effects over the material properties? So this is for the second part, just to explain the influence of every one of these imperfections over the plastic deformation and the mechanical properties of the nanocrystalline material. So let us start first with the point defects, like vacancies, interstitial, substitutional atom. We said that we do have a substitutional atom here, we do have some vacancies. So what is the contribution of these or the influence of these point defects on the material microstructure and mechanical properties and the plastic deformation? So as we discussed in chapter 4, even we have mentioned this in chapter 7, like the existence of substitutional atom, because to have another substitutional atom of an impurity, this indicates an alloy. So this definitely, this type of the nanocrystalline material should be alloy. Then you can explain simply the strengthening mechanism due to alloying, because we are expecting, because of the existence of this substitutional atom, we are expecting that the strength of the material is going to increase, the ductility could be decreased because of the lattice strain that is going to be imposed or generated within this grain because of this substitution atom. But something that you should understand, that these point defects are related within one specific grain, within this grain itself. It won't gonna be exceeding to cover the whole material or even to the grain boundary. Here this is just only relevant to the one single grain. Like here we do have substitutional atoms within this grain, we do have vacancies within this grain. So these point defects will impose lattice strains on the surrounding atoms within this specific grain. The lattice strain field will interact with the dislocations, resulting in an impedance of the dislocation motion. As we explained in chapter 7, these lattice strain will interact and impede the dislocation to move, and this definitely will affect the mechanical properties of the material. So we are expecting, because of these defects, that the tensile strength of the material, the yield strength of the material will increase, but on the other side, the ductility are expected to decrease. Because of what? Because of the dislocation impedance that will be generated because of this lattice strain. So this is for the influence of the point defects. So nothing new, as we explained in chapter 4 and in chapter 7. This will produce lattice strain and impede the dislocation motion. But how about the line defect? If there is a line defect that like dislocation, as I mentioned, this figure doesn't represent any dislocations, but if there is a dislocation exists, definitely it would affect the mechanical properties and the microstructure of the material. So the dislocation produces lattice distortion, as we explained in chapter 4. We said that the existence of a dislocation like edge or screw dislocation is going to produce a lattice distortion which should be local, and this lattice distortion decreases as we go far from the existence, the dislocation line itself. But anyway, it will impose some lattice distortion and it will impose some lattice strain. The dislocation will impede the motion of one another, and in addition, this lattice strain that will be produced because of the dislocation is going to inhibit or is going to impede the dislocation of the motion of another dislocation. The increase in the dislocation density, the increase in the dislocation density inside the material microstructure, and this is something that we could expect for nanocrystalline material because of the severe plastic deformation. It will increase the dislocation interaction, and the dislocation may overlap, and in the meanwhile the strengths will increase, but the ductility on the other side will be decreased. So these are the changes over the microstructure and the mechanical properties that we expect because of a line defect that would be exist inside the microstructure of a nanocrystalline material. In addition to these line defects and point defects, which nothing new so far, what about the interfacial defect as a grain boundary? We said that the interfacial defects are two things: grain boundaries and the surface of these grains and the surface of the pores. So the interfacial defect that comes, just let us focus over the grain boundary first. As we said here, These atoms, these black atoms represent the atomic structure of these grains. And as you can see, the grain boundary has a random atomic structure. Atoms within the grain boundary, very random. And the atomic spacing, another thing, that the spacing, which is the distance between the atoms that form the grain boundary, is larger than the atomic spacing in the grain. And if you recall, in chapter 6 or even before that, in chapter 3 and chapter 2, we discussed that everything is related to the material microstructure. All the properties of the material related to the atomic structure and the microstructure of the material. So as long as there is a difference in the space or the distance between two atoms that form the grain boundary than the spacing between the atoms that form the grain, so we are expecting that the mechanical properties of the grain boundary will be different than the mechanical properties of the grain. If we just gonna observe, assume or think that this grain is different than the grain boundary. So in this case, you could deal with the grain boundary like it is a totally different material inside the material microstructure. The grain has its own material properties, while the grain boundary, it has a different mechanical properties. Despite both are representing and forming one single specific material, but here, since the atomic structure of the grain boundary is different than the atomic structure of the grain core, we are expecting that the mechanical properties of the grain will be different than the mechanical properties of the grain boundary. So since the spacing, the atomic spacing and the atomic structure of the grain boundary is larger than or different than the atomic spacing in the grain core, this makes the grain has mechanical properties which are different than the properties of the grain itself. So what does it mean this? It means that we're gonna end up with a heterogeneous microstructure. The microstructure won't gonna be uniform anymore. We don't have heterogeneity. We don't have inhomogeneous material microstructure. The property, if it is probed and measured at any point, will be different from one point to the other point. We don't have totally a heterogeneous microstructure with different mechanical properties that will be different from the grain boundary than the grain itself. So also, we are expecting that the elastic modulus and the strengths of the grain boundary are lower than those of the grain. Why? Because the spacing between the atoms within the atoms that form the grain boundary is bigger than the spacing with the distance between atoms that form the grain. So what does it mean this? This mainly because of the bonding. The bonding between the atoms within the grain core is very strong in comparison to the bonding that exists between the atoms that form the grain boundary. Or the type of the atomic interaction between the atoms that form the grain boundary, it is lower than the interatomic interactions that generate between the atoms that form the grain core. This makes the grain more stronger than the grain boundary itself. So based on this investigation and understanding of this microstructure, we can say that the elastic modulus and the strengths of the grain boundary are in general lower and smaller than the strength and the elastic modulus of the grain core itself. This is based on so many studies that I have made and so many other people have done over nanocrystalline material. It was demonstrated that the elastic modulus and the strengths of the grain boundary are in general lower than those of the grain. I have studied the elastic modulus and the strengths in one of my papers published in Mechanics of Material. I have demonstrated explained how the elastic modulus, how the strengths of the grain boundary, it could be tailored or changed. Basically, in case that we are talking about a nanocrystalline material, in many of the cases is going to decrease. Both they are going to decrease for the grain boundary than the grain core itself. And this will end up with a heterogeneous material microstructure. So this is one of the changes over the material microstructure because of the grain boundary. Also, the grain boundary, as we discussed in chapter 7, it impedes the dislocation motion. We said that the grain boundary, it works like obstacle for the dislocation to leave one grain to another grain. Why? We mentioned two reasons for this. One reason that because the two grains which are found side by side, the dislocation have to change its direction of motion would it transfer to another grain because of the misorientation. We do have one grain with a specific crystallographic direction, and the slip direction in one grain will be different than the next grain. So the dislocation should orient itself to move to the next grain following its slip system, and in that case this requires that we have to give more energy, and this indicates more strong material. Another reason is because of the atomic randomness or the atomic disorder. As shown in the figure, atoms are very random within the grain boundary region. This results in a discontinuity in the slip plane, as we mentioned in chapter 7, from one grain into the other grain, and this what make the strength of the material is going to increase. So as a result, this increases the material strength. So if the material strength is going to increase, what we should expect about the ductility? As we mentioned in chapter 7, and even as it was mentioned in the textbook, in many of the cases the ductility is going to decrease. But this is not necessary to be the case. We could achieve enhancement in the ductility and the strength, both of them in the same time. Especially if we're going to make this nanocrystalline material, and this is one of the contribution, one of the things that I have revealed in my recent study about the correlation between the grain boundary and the mechanical properties of these nanocrystalline material. We have demonstrated that we would be able to enhance both the strength and the ductility if we could able to achieve this nanocrystalline material. So the reason is because the grain boundary has a lower elastic modulus, as we mentioned, since the spacing between atoms is bigger, so the elastic modulus of the grain boundaries it is lower than the elastic modulus of the grain core. This makes the grain core more rigid than the grain boundary. The grain boundary becomes more like kind of elastic, you could think of it like it is more flexible. So the overall elastic modulus of the nanocrystalline material in general, because the grain boundary has lower elastic modulus, will be decreasing. For example, if you're going to compare the elastic modulus of a polycrystalline material that has grains in the microscale to the elastic modulus of the same material but it is nanocrystalline, like we do have the same material type, one with microscopic grains, the other one with nano grains. The one with nano grains will have a Young's modulus, or its elastic modulus or Young's modulus will be lower, will be smaller than the one with microscopic grains. Why? The reason is because of the grain boundary. The grain boundary has a lower elastic modulus, and in the nanocrystalline material state, the grain boundary contributes around 50% of the material microstructure. So it will have a significant contribution on the material mechanical properties, and one of the things is going to severely decrease the elastic modulus of the material. Another thing, as an effect of the grain boundary, because of the grain boundary has a lower elastic modulus, it would also allow for the grain rotation and motion. As I said, the grain boundary is kind of flexible. It's kind of easy to move. It's gonna work like an easy spring. So this will make one grain can easily rotate and move between with respect to the other grains. This easy movement of the grains, as we explained today and over the previous videos, as you allow for the easy rotation and motion of the grain, this indicates a more ductile material. So therefore, we are expecting that the ductility is going to increase and enhance it. So using this nanocrystalline, this is a good thing. This is a very interesting observation. Like, because of the nanocrystalline material, we can achieve enhancement in both the strength and the ductility. While the strength of a nanocrystalline material increases, because of what? Because, as we mentioned, because of these imperfection, the grain boundary is going to work like an impedance to move the dislocation, to allow for the dislocation to move. And because of the atomic disorder, it would be difficult for the dislocation to swing and orient itself between, and this will result in a discontinuity in the slip plane. This requires more energy, and that's why the strength overall of the material is going to increase, because it would be difficult for the dislocation to move inside the material microstructure. But in the meanwhile, the ductility is going also to be increased. Why? The reason is because that the grain boundary has a lower elastic properties that would make easy for the grain to rotate and move inside the material microstructure, and indicating an enhancement of the material ductility. So it is a very good and important contribution and observation about the grain boundary and how it would contribute to the mechanical properties of a nanocrystalline material. Another interfacial defect is the surface of the grain, which are these sky atoms, these atoms that located and distributed over the grains, or even the atom, as we explained, that would be located over the exterior of the bore. So what is the contribution of these atoms? This is considered as a defect as is explained in chapter 4. So atoms at the grain surface, the same thing, atom that located over the grain, the boundary of the pore, are underbonded, as we mentioned in chapter 4. Therefore, these atoms are in a higher energy state than any other atom that located inside the grain core. So these atoms will have higher energy than the other atom that located inside the main core of the material, and that's why this difference in the energy, as we mentioned in chapter 4, it will be counted as a crystal defect, as one of the material imperfections. Another thing, this results in an excess surface energy which tends to deform the surface. This extra energy of the surface is gonna achieve some deformation and lattice distortion, but over the surface. And that's why, again, it is counted as a defect. The deformed surface, in addition to this excess energy, definitely they are going to impede the dislocation to move through the grain surface. If there is one grain that would like to leave this grain, if there is a dislocation that would like to leave this grain to the next one, it have to go through the surface of the grain, but it won't gonna be that easy because of the extra energy, because of the lattice distortion over the surface. This gonna make the dislocation be difficult to move through this surface with extra energy, and this will impede the dislocation motion, and accordingly the strength of the material, whatever it is, yield or tensile strength of the material, both are going to increase. Because of what? Because of this extra energy that comes from that generate over the surface of all of these different grains. So this also explains why the strength, the overall strength of nanocrystalline material increases. This is because of this reason, because of the surface of the grain. So one reason is the grain boundary itself. It has a very random atomic structure that make it difficult for the dislocation to swing itself and orient itself to move. The second reason for the increase of the strength is the surface energy of the grain surface that would impede the dislocation to move from one grain to the other grain. Make sense? The last defect here that we have is the volumetric defect. What is the effect of this volumetric defect as pores or voids that would be generated inside the material microstructure of a nanocrystalline material on its properties and microstructure and the dislocation motion? So pores may result in a lattice distortion, very similar to the basic idea of the vacancy. But the vacancy, it is a pore, it is a cavity, it is a missing atom but within one specific grain. So we can even deal with the vacancy like it is a pore, but it is internal, within one specific crystal, one specific grain. So it will be counted like a vacancy. And as we explained in chapter 4, the vacancies, these are point defects that could result in some lattice distortion. The pores, which are the voids that would be located somewhere within the material, and it is not necessary to be related to one specific grain or crystal inside the material microstructure, it will be considered as a volumetric because it will be seen from the volume form as a volume, because it is going to form like a sphere that is empty within the material microstructure. So even we can deal with it like it is a vacancy, but over the general microstructure of the material. And in that case, it will also produce some lattice distortion and local lattice strain, very similar to the vacancies that we explained in chapter 4. So it should do the same effect as the conventional vacancies. So this lattice strain definitely will impede the dislocation motion, and accordingly, we should expect an increase in the strength because of the existence of these pores inside the material microstructure, as long as these pores are going to strengthen the material by impeding some dislocation. Make sense? But in some cases, in case that the fraction of these pores has been significantly increased, the material would be weaker. The material could be, the strength would be decreased because of another mechanism. But if these pores, as long as they are going to impede the dislocation motion from one grain to the other one, this definitely will result in a slight increase in the strength of the material. In the meanwhile, the overall elastic modulus of the material is going to decrease. Why? Because this cavity, it is void. And this void kind of weaken the material, reduce the elasticity of the material, because you are subtracting more elasticity from the material by removing the material itself, by forming voids and cavities inside the material microstructure. So we found that as this Bohr fraction increases inside the material microstructure, the percent or the concentration of this Bohr, as it is increases, the overall elastic modulus of the material is going to decrease. And these are the effects of the Bohr as volumetric defect on the mechanical properties and the microstructure of the nanocrystalline material. So this example, it is a very interesting example to understand how what are the microstructural changes, the mechanical properties, and the effects of these imperfections. So as you can see, to answer this question, we had to go over chapter 4 and chapter 7 through that we covered in this course so far. Make sense? All right, so one more example that already found in the exercise sheet and also in the homework is just to refer to one of my papers that already published in Material Science and Engineering A, which is one of the top 10 journals in the material science field and materials engineering. These figures are already published in this journal, and if you refer to this paper, you're gonna find that we already processed a pure metal by accumulative rod bonding. Accumulative rod bonding, it is very similar to the rolling. It is just like the conventional rolling process that I explained in the beginning of this video. But we are not just doing one cycle of rolling, but instead we are doing multiple cycles of rolling. As we said that if we repeated the rolling process, we are going to severely deform the material and we are going to achieve some severe plastic deformation. So the accumulative rod bonding process, it is one of the metal forming processes that mainly used to bond two materials together. So it has a certain approach. There is no need to understand it with more detail, but anyway, the key condition that you should understand that this material has been rolled, and it has been cold rolled, and the material, it is pure copper. So we processed pure copper material by cold rolling. We rolled this material sample one cycle, second cycle, third, fifth, and so on up to 7 cycles. So we have performed 7 cycles of rolling over this pure metal. So definitely after the first cycle, as I explained before in this video, in the beginning, this pure copper, it has a certain amount of dislocation density, which is going to be very small, around 10 to the power 3 as a pure copper. Then after the first cycle of the rolling process, we are expecting that the dislocation density, it will be significantly increased. Then after the second cycle is going to increase further. Then it could reach to some saturation somewhere, somehow, right? But anyway, or it could be gonna keep on increasing. It depends on the material type. It depends on so many things that would be located and defined inside the material microstructure. And even it depends on the way and the strain, the rate of the plastic strain. So there are lots of details. I won't gonna go through these details, but the thing that you should understand that we have carried out this rolling process multiple cycles. So we have done one cycle, second up to 7 cycles of the rolling processes. And then for every cycle, we measure the mechanical properties of the material in terms of field strength, tensile strength, hardness, the micro hardness of the material. This is one of the mechanical properties that we define in chapter 6. And also we measure the ductility of the material. And we have extracted some results that already represented in these 3 figures. So the objective is just to explain the changes over the material microstructure and the changes over the mechanical properties of this pure copper that has been processed by accumulative rod bonding based on these 3 results, based on these 3 figures. Make sense? So let us read the figures first, one by one, and understand what these figures are. So the first figure here on the left, this one, it gives the relation between the dislocation density over this vertical axis and in the meanwhile the crystallite size. The crystallite size, it is somehow related to the average grain size. As we decrease the crystallite, which indicate the crystal size, it is related to the crystal size. So as we are decreasing the crystal size, we are expecting a decrease in the overall grain size. So you could deal with the crystallite size like it is a decrease or a change in the grain size. Make sense? In the meanwhile, we do have the dislocation density. In the meanwhile, over this right vertical axis, we do have the lattice strain. This lattice strain can be obtained by something that we call as RD analysis. We can identify and measure how much of lattice strain has been generated because of the dislocations, because of the distortions that would be found within one specific grain of this material, of this pure cover. So these are the lattice strain that we already measured. So we measured this data experimentally based on the XRD analysis and TM analysis in addition to the lattice strain from the XRD analysis. But anyway, these are the experimental results as already given to us. So as you can see in this figure, this row indicates the dislocation density as you can see here. And if you just track the curve, the line or the curve for the row, which is with a star, so as you can see, you're going to find that the dislocation density is going to keep on increasing versus the number of cycles of accumulative rod bonding. So the zero cycle indicates that we didn't do accumulative rod bonding over this pure cover. But after one cycle, as you can see, the dislocation is going to increase. After the second, it's going to keep on increasing. After the third, even after the fourth cycle, is going to significantly increase after the sixth cycle. But between the sixth and the seventh, if we have done, when we have done one more cycle after the sixth, we end up with a slight decrease in the dislocation. So these are the changes in the dislocation density as we measured it or determined it from the XRD analysis of these different samples after the different cycles of the accumulative rod bonding. As you can observe, before processing, before rolling, as we explained in the first example, before rolling, the dislocation density, it was around 80 times 10 to the power 13 meter to the power -2. If you decided to convert it into millimeter, you should divide the 10 to the power, you should divide by 10 to the power 6. So this is gonna give us at the end 10 to the power 7. So it is gonna be around 80. In total, it's gonna be like around 8 times 10 to the power 8 as a dislocation density millimeter per second, millimeter to the power -2. If we are, this is the dislocation of the pure copper before rolling. So as you can see, this copper metal, it is initially from the beginning, we're already getting it with a very high dislocation. No problem, but anyway, we're gonna keep on increasing the dislocation after the accumulative rod bonding. So for example, after 2 cycles, it had been increased like around 125 times 10 to the power 13 meter to the power -2 as dislocation. After the 4th cycle, it has been increased. After the 1st, 5th, and so on, then as I mentioned, there is a slight decrease in the dislocation. So these are the changes over the dislocation density because of the rolling. Can we explain these changes over the dislocation? What is the reason behind it? Yes. Typically the same as we explained before for the rolling operation. You can deal with this example like it is, like the first example, that you just gonna explain the changes or the microstructure before rolling and the microstructure after rolling. What are the changes? So before rolling, as we mentioned before, the microstructure is uniform. The grains are equal axed. In addition, the dislocation density, it was low. But after the rolling, and as we do, or as the number of the accumulative bonding cycle increases, the dislocation density is going to increase. And we're going to have a continuous increase in the dislocation density upon the increase of the number of the accumulative bonding cycles, except for the last cycle, we're gonna have a slight decrease in the dislocation. The reason behind this is lots of things. One of the things that are the grains. After the first cycle, it will be elongated. After the second cycle, it will be elongated further. After the third cycle, the grains will start to be broken down. We're gonna start another phase of the grain structure as grain subdivision. That we're gonna end up with subgrains that will be formed inside the material microstructure. And as we further reduce or apply plastic deformation by rolling over these subdivided grains, this will multiply further the dislocation density inside the material microstructure. So again, something that you should understand, that I have mentioned this in the video today, that any material will reach to a saturation state of its dislocation density. Like as I mentioned, after the first cycle, and this is what we are expecting for any conventional material. After the first cycle, we are expecting that the dislocation will be significantly increased. After the second one will be increased till it will reach the saturation case. Then after, as long as you do any more cycles, we are not expecting any more increase or significant increase in the dislocation density. But this is not the case for the processed pure copper here. As you can see, as we do further accumulative rod bonding, we are multiplying, and there are even more increase in the dislocation, and even the dislocation increases further and higher. The reason, so there are two things that you should observe here. One of the things, between the cycle 0 and cycle 4, we do have a certain rate of increase. We have almost like straight line, right? Then from 4 to 6, the rate has been increased. It means that the dislocation has been increased significantly. It means that there should be something happen to the material microstructure after the 4th cycle that makes the dislocation further increase. In the conventional case, the material after the 4th cycle, let's say, it should reach to the saturation case. It means that the curve should continue horizontal, indicating a saturation state of the dislocation. But this didn't happen. So what is the reason? The reason is the grain subdivision. Initially, up to the first 3 or 4 cycle, the grains were gonna keep on elongating because of the rolling process. As we do rolling, the grain will be elongated further. Till the grain subdivision, after the 4th cycle, the grain subdivision is gonna come into play. The grains will be divided, will be small in size, and this will result in more generation of new dislocations within the newly formed and subdivided subgrains. Because of the grain subdivision, this is the main reason that make the dislocation between cycle 4 and 6 further and more increase. So we can answer this part as observation of the dislocation density from cycle 0 to, or after the first 4 cycle, the dislocation has been increased. The main reason behind the increase in the dislocation within this part is the strain hardening. So the main reason here is the strain hardening. As we explained, strain hardening, it means that because this material has been processed at room temperature, we have done cold rolling to this pure copper. So because of the strain hardening, which is related to a multiplication of the dislocation, it is expected to increase within the first 4 cycle. Then it should reach a saturation state, but this didn't happen. Why? This indicates there is another mechanism that came into play, which is the grain subdivision. So within the other cycle or the other range between the 4th cycle and the 6th cycle, we're gonna have another mechanism, which is the grain subdivision. Because of the grain subdivision, we're gonna end up with more dislocation that is going to be increased and increase more, and this would result in an increase in the dislocation density. But while the dislocation between the 6th and the 7th cycle has been decreased, this indicates a recovery. We said that the recovery, which is one of the annealing, and if you recall over the previous video, we said that the recovery, it is not necessary to be done by heating the material. The recovery could be done usually without heating the material. And this is what we observe it here. The dislocation of the density indicated a recovery of the material. And to prove this, we had observed a decrease in the lattice strain. So we do have a third range. And within the third range here or region, we're gonna have a recovery. This recovery indicates a slight decrease in the density. As you can see, the density is slightly decreased. So these are the changes over the material microstructure in terms of the dislocation density from this figure. How about this blue curve? Or let us just explain this brown curve. This brown curve, this is the lattice strain. So as you can see, the lattice strain was high before processing. After we process, the lattice strain is going to keep on decreasing, which is something that could be strange, because as we form more dislocations, we are expecting there should be some more lattice strain that is going to generate. But this is because of something that we call as a stacking fault energy of the copper. The copper is known as that it has a low stacking fault energy that allow the copper to relieve any residual stresses automatically. But anyway, because I don't want to give you more detail that would confuse you. But anyway, if we start from the beginning, we're gonna observe as decrease in the lattice strain within the first 4 cycles. But the interesting here is that between 4 and 6, we're gonna end up with an increase in the lattice strain. This increase in the lattice strain indicates that we're gonna have further more dislocations have been formed. So within the first region, within the first 4 cycles, during the strain hardening, and because the copper has low stacking fault energy, the lattice strain was decreasing. But then after that, between the 5th and the 6th has been increased because of the grain subdivision. It came into play within these 2 cycles. And this would result in a formation of new dislocations, and that's why the lattice strain has been increased. So the increase in the lattice strain here, it is mainly because of the dislocations that produce lattice distortions and lattice strain within these single grains. Then between the 5th, the 6th and the 7th cycle, within the last cycle, we end up with a recovery and a slight decrease in the dislocation, and in the meanwhile, we end up with a decrease in the strain, in the lattice strain, which indicates a recovery. As we explained, the recovery indicates a relief in the residual stresses, a relief in the lattice strain. We're going to end up with a decrease in both the lattice strain and the dislocation density, and this is what we typically obtained in this figure. Make sense? Another thing, which is the third curve. As you can see, this blue curve, just observe this curve. This curve indicates the decrease in the crystallite size. We said that this is like the grain size. So according to this curve, the grain size was initially like around, above 110 nanometer. But after the first cycle, the second cycle, third cycle is going to keep on decreasing. So we're going to have a continuous decrease in the grain size with the further processing of the or further rolling of the pure copper by accumulative rebonding. So as we increase the number of cycles, the grain size is going to increase. So these are the data that we can understand and extract from this figure. Make sense? So, based on this discussion, what we should expect as it changes over the material yield strengths, tensile strengths, and hardness. You should understand that these 3 mechanical properties, so these are the changes. This figure, we can explain through this figure the changes over the material microstructure. But what are the changes over the material mechanical properties like yield strengths, tensile strengths, micro hardness, and ductility? So this figure explains the ductility or the changes over the ductility. Here, these are the changes over the yield strengths, micro hardness, and tensile strengths. It is very simple, as you can observe and as you can see. We gonna end up with a continuous increase in the 3 parameters, in the 3 mechanical properties, the yield strengths, tensile strengths, and hardness. All of them are increasing as we are increasing the number of the accumulative rebonding cycle. What is the reason? The reason are the strengthening mechanisms. So how many strengthening mechanisms that found here? We do have only 2 strengthening mechanisms. Why? Because we didn't do alloy. We do have a strain hardening. Why we do have a strain hardening? Because we are doing or performing the accumulative roll bonding at room temperature. So we do have a strain hardening that is conjugate to the multiplication of the dislocation. As you can see, the dislocations are increasing with the number of cycles, indicates an increase and impedance, and these dislocations are overlapping and they are impede each other. That's why we're gonna end up with an increase in the strength. Another reason is that because of the formation of small grains, because of the grain subdivision, which especially is going to take place between the cycle 4 and 5, this is going to give a further increase in the strength and the hardness of the material. Why? Because of the grain subdivision that is going to generate new grain boundaries with high angle grain boundaries within the cycles 5 and 6, and that's why within the third range, as you can see, I'm splitting this figure into 3 regions. Within the middle region, we're gonna end up with an increase in the dislocation. Increase in the number of the high angle grain boundaries, and this what increase the strength is gonna keep on increasing the strength of the material. Within the last region, the strength almost, as you can see, for example, one of the curves is gonna be like kind of constant, or we would end up with a slight increase in these properties despite we do have a recovery. But as I said, the recovery is going to relieve somehow the lattice strain, is going to relieve somehow the dislocation density, but the recovery is not that effective to significantly decrease the strength of the material or even the tensile strength of the material. Make sense? So that's why in general, this figure indicates that we're gonna have an increase in the strength, tensile strength, and micro hardness as we increase the number of accumulative roll bonding. And the reason is because of 2 strengthening mechanisms. The first one is the strain hardening because of the multiplication of the dislocation. The second one is because of the formation of new grains due to the grain subdivision with high angle grain boundaries. Make sense? How about the ductility? As you can see in this figure, I'm presenting the ductility beyond the first cycle. Something that you should understand, after the first cycle of this pure copper, the ductility had been decreased significantly. We're going to end up with a significant decrease in the ductility, and we know the reason. The reason is because of the overlapping of the dislocation and the formation of more grains. This and lattice strain, this is going to make it difficult for the grain to glide to each other or to move with respect to each other. This is going to make the ductility difficult, as we explained in the beginning of this video when we were discussing the changes over the ductility due to cold rolling. So we are expecting after the first cycle that the ductility will be decreased significantly. But the question is, can we show some enhancement or increase in the ductility after the second or the third and fourth cycles? Yes, we can. And this is what we have achieved in this study. That we achieve an increase in both the strength and enhancement in the ductility after the first cycle. After the second cycle of the accumulative roll bonding, the ductility had been increased. This was the ductility, very small. It was very, very small after the first cycle, but now it had been increased. So these are the enhancement. We enhanced the ductility around over 50% of the ductility has been increased and recovered after the first cycle. After the third cycle, we do have a slight decrease, and then we're gonna end up with an increase. Then we're gonna almost have like a constant curve of the ductility. Okay, so if we have done like a fitting, we're gonna end up with this curve that indicates the changes over the ductility over the different during the accumulative roll bonding processing. This dashed curve indicate the changes in the lattice strain, the same change. So between the first 4 cycles, we do have a decrease in the lattice strain, then we're going to have an increase in the lattice strain, then we're going to have a decrease on the other side as a relief of the lattice strain. So the question is, why the ductility has been increased as we further accumulative roll bonded this pure copper? So let us start from the beginning, from the first. After the first cycle, we said after the first cycle, we said that the ductility will be significantly decreased. The main reason behind the ductility, so the ductility will be decreased significantly, and the main reason behind it is the strain hardening. As we said that the strain hardening, as we explained on the effect of the cold rolling, you just gonna explain the same. The ductility will be decreasing because of the strain hardening. The main reason that the strain hardening is going to multiply and increase the dislocation density inside the material microstructure. And as these dislocations are increasing, they're gonna be overlapping, and this will result in a decrease in the ductility as we explained before. And so after the first cycle, nothing new. This is what we are expecting. But the strange thing, why the ductility has been increased, as if you try to track the curve, this curve that indicates the trend of the increase, so indicates an increase in the ductility within the first to the fourth cycle. So within the first to the fourth cycle, we're gonna end up with a decrease in the ductility. The ductility will be increasing. But so what is the reason? The reason is two things. The reason first, that the low stacking fault energy of copper. Copper, it has a low stacking energy, and something that is well known for any material, that the ductility somehow is related to the stacking fault energy of the material. That is one of the lattice properties of any material. I won't gonna explain it because I don't give you more details. But anyway, in case that you have a material with a low stacking fault energy, the ductility of this material is more likely to be ductile. So copper by default, it is a ductile material, and this is what we knew about copper material. As we explained in the beginning of this class, all the electrical wires are made of copper, and that is fine to bend and stretch and twist a copper. A piece of copper, and it won't gonna be fractured, indicating that it is very ductile. The main reason that is one of the reasons that it has low stacking fault energy. So copper has a low stacking fault energy, and this what give ability to the copper to enhance the ductility or build the ductility. And another reason is the decrease in the lattice strain. As we said, the lattice strain is going to decrease, as we explained over this figure. As you can observe, this lattice strain is going to keep on decreasing within the first four cycles. This decrease indicates a relief of the residual stresses inside the material microstructure, and also this indicates that despite we do have an increase in the dislocation, the overlapping between these dislocations will start to be relieved. Or in other words, we can say that these dislocations somehow they are aligned together in such a way to give an enhancement in the ductility inside the material microstructure and allow for the rotation and the deformation of the grains inside the material microstructure. Make sense? So this is within the first four cycle. This explains why we're gonna end up with an enhancement in the ductility. But within the fourth to the sixth cycle, we're gonna end up with a slight decrease. As you can see, the ductility has been decreased slightly within this four cycle. The main reason behind it is that the dislocation, multiplication, and the strain hardening is gonna come into play one more time. We're gonna end up with more dislocation. They're gonna be forming within this figure as observed here, and this would result in an increase in the lattice strain. So they're more overlapping. This indicates that the dislocations within this period, within this region, they are more overlapping together. And they are going to impede each other, and they are going to impede the motion and the rotation and the motion of the grains inside the material microstructure, indicating a decrease in the ductility. And this what explains the ductility within the second region. So within the second region, why the ductility is decreasing? Because of the overlapping between the dislocation and the increase in the dislocation density, which will result in an increase in the lattice strain. As you can observe, the lattice strain has increased, indicate that more dislocations are generated, indicate that more overlapping are generating, indicate that more lattice strain is generated, and all of these things impede the motion of the grains inside the material microstructure, and this what decrease the ductility within the second region. So within the first region, why the ductility has increased? Because from the beginning, After the first cycle, why the ductility has severely decreased? Because of the stacking, the strain hardening. Within the cycle 1 to 4, the first region, why the ductility has increased? Because of the low stacking fault energy of the copper and the decrease in the lattice strain. Which indicate that there is no significant overlapping between the dislocations. We do have more dislocations, but they are not overlapping together. So that's why the lattice strain was decreasing, and on the other side, the ductility has been enhanced. But within the second region, the ductility has decreased. The main reason behind it is more overlapping has been generated between the dislocations, which resulted in an increase in the lattice strain and more impedance for the grains to glide or to move or to rotate inside the material microstructure, indicating a decrease in the ductility. But within the third region, as you can observe, the ductility has increased. Why? The reason behind the increase in the ductility within the third region is the recovery, as we mentioned. Here, we end up with a recovery within the third region. That's why we end up with a relief in the residual stresses or the lattice strain at a slight decrease in the dislocation. So this gives a recovery, and as we explained, the recovery is going to slightly increase the ductility, and this is what happened. We already end up with a slight increase in the ductility within the third region. So as you can see, all the results and the figures are consistent together and explain what we already have covered in chapter 7 and even in chapter 4 about these different effects of these dislocations and these different microstructure defects on the mechanical properties of a pure metal that has been processed by accumulative rod bonding at room temperature. Make sense? Alright, so let us consider this example about the TM micrographs. So these are images of the transmission electron microscope of some material or of some material sample that already made of pure aluminum. So it is another metal, pure metal material. The pure aluminum, it is very weak material, and if we are going to decrease the grain size or convert it somehow into ultra fine grain material, we are going to end up with some enhancement in the mechanical properties of this pure titanium. And this is what already have been done by these professors who already studied in 2001 the influence of the Ecap roots on the microstructure and properties of pure titanium. So Ecap, it is one of the severe plastic deformation processing, very similar. It do the same thing like the accumulative rod bonding, but the technology is different. But anyway, it's gonna almost have the same influence on the microstructure like the accumulative rod bonding. But the Ecap, very quick just to understand it, that we are forming a channel. This channel, it is angular, so that's why we got the equal channel angular processing. So it is the Ecap. These are the abbreviations for the title or the name of this process. As I said, we are going to form a die. This die should have like a channel. This channel is gonna be angular. It has like an angle. Then we are preparing a sample of this pure titanium, and then we are pushing the material sample to go through this channel, so it will be angled. So this is the entrance, and it will be exit from this side. Upon this process, so this is one cycle of the Ecap processing. Upon this process, we are achieving severe plastic deformation over the material, and this would result in a reduction in the grain size. And at the end, after 2, 3, 5, or 8 cycles even, we're gonna end up with an ultra fine grain material that the grain size, it will be severely decreased to the micro, to approach hundreds of nanometer. Like we can degrade the grain size up to 300 nanometer, 200 nanometer in some cases, if we decided to use this Ecap as one of the severe plastic deformation processing. So in this study, these guys already, they used Ecap to process pure titanium to refine the grain size into few hundreds of nanometer that has been processed by severe plastic deformation using Ecap processing. The image on the left, this image on the left, shows the microstructure of the titanium after the 8 cycles of Ecap processing. So we have done this Ecap processing 8 times, 8 cycles, and we end up with this microstructure that we got this image using the transmission electron microscope. So this is known as TM image of the material microstructure. These things, these details indicate that you do have microstructure and there are lots of grains. We can identify, for example, as you can see, this could be represented as one single grain. So I'm just going to give you something just to allocate one grain. So this is one grain, and there should be another grain here, and this is another grain and another grain, and so on. So as you can see, we can somehow observe the grain boundaries between these different multiple grains. You got my point? So this is after 8 cycles of Ecap, we're gonna end up with this microstructure. Remember that any pure material in the conventional state, its microstructure, as we explained for the case after cold rolling. Before rolling, it's gonna be the same thing. Before Ecap, we should have a uniform material microstructure. The microstructure should be uniform. The grains, it should be equal axed. They do have the same size in all directions, and it should be like kind of cubic somehow. But as you can see, after the 8 cycles of Ecaps, the grains somehow are elongated in a certain direction. Very similar to the thing that we have achieved if we decided to apply cold rolling over the material. We said that due to the cold rolling, the grains will be elongated over the material microstructure. So the question is, anyway, this image showed the material microstructure after 8 cycles. This image on the right represents the microstructure, the TM of the microstructure after each cycle of the Ecap followed by annealing. So after we do annealing, we're gonna end up with this microstructure. Before we do the annealing, just only 8 cycles of Ecap, we're gonna end up with this microstructure. So the question is, so the image on the right, as I mentioned, showed the microstructure of the processed titanium, but after annealing. In reference to these two images, explain the changes of the material microstructure and the mechanical properties of pure titanium due to these processing conditions. So the thing that we should expect, in general, we already have answered this question before for the cold rolling process. So the answer is going to be almost the same, but your objective is just to try to refer and map this explanation to what you can observe from these two images. For example, one of the things that we should expect, let us work first over these 8 cycles of Ecap. So the original material microstructure, as I mentioned, it should be uniform. The grain should be equal axed. The material, it should have the dislocation density, it should be too small, or the dislocation is too small. In this pure titanium is going to be like around 10 to the power 3, 10 to the power 4 millimeter times to the power -2. And this is what we conventionally can observe for this pure titanium. So before Ecap processing, so you have to explain what is the material microstructure. Let us focus first over the material microstructure before Ecap. So before Ecap, the microstructure is uniform. The grains are equal axed. The dislocation density is low. It is around 10 to the power 3 millimeter to the power -2. This is the microstructure before Ecap. After 8 cycles of Ecap, what you can see from this microstructure? One first observation, that the grains are elongated. They are not equal axed anymore. They are elongated in a certain direction that depend on the process and the method by which we're already performing this Ecap process. So this is one observation. From the figure on the left, we can observe that the grains are elongated in a certain direction. All the grains, if you can observe, try to allocate one grain. So this is like one specific grain, and there should be another grain. So as you can see, it is kind of elongated in a certain direction. It's going to be much more clear over this one. This is one change over the material microstructure after Ecap. Another change, as you can see in the figure, there is a high contrast. There is a high difference in the color of the grains. The TM, it works with the concept of white and black, like it's gonna represent, it depends on the lattice strain. It depends on the, as if you don't have a grain that the lattice strain within this grain, it is very high, it will be seen, or it will be seen black and dark within the TM micrograph. So these dark grains, if for example, if you're gonna compare this grain to the next one, this is very dark, this is kind of white. So this indicates that this dark grain, it is filled with dislocations. There are lots of dislocations that overlapping inside this single grain, which is seen as dark grain. But the one, the grain with a white color, kind of, there are some dislocations inside it. The dislocation, for example, can be observed here. As you can see, this dark area indicates there are some dislocation. This one indicates there are some dislocation. So these dark areas indicates dislocations and indicates lattice distortion and lattice strains. So as you can see, there is a contrast. This contrast, as I mentioned, indicates that there are some of the grains that will be filled and crowded with dislocation, while some other grains definitely they won't gonna have that much of dislocation like the others. So this indicates that there is non-uniform microstructure. So one observation that the grains are elongated in certain direction. Another observation is that the grains, some of the grains will have so many dislocation, or the dislocation density within specific grains is different. There is a huge contrast in the color that indicate that is non-uniformity. The microstructure, it is non-uniform. Another thing, as you can see, the grains with the dark spots and dark areas, they are so many. This indicates that the number of the dislocation density has been increased significantly. How much? This requires some other software that we can use to do analysis for this image, or even using the XRD, we can determine how much of dislocation density is. But for now, you don't have this information, so the only thing that we can say that based on the contrast and as seen in the figure, that the grains are filled with so many dislocations that indicates that the number of the dislocation density has been significantly increased after 8 cycles of Ecap. This is another third observation that we can see from this figure. Make sense? So these are the changes, you could say, these are the changes that we can observe from this figure over the material microstructure if we're going to compare the titanium that is processed by 8 cycle in comparison to the pure titanium. So the pure titanium has a uniform microstructure and the grains are equal axed. The dislocation density is low, but here the dislocation density after 8 cycle, it is significantly increased as shown in the contrast and the dark spots and grains within the material microstructure. In addition, the contrast indicate that there is non-uniformity inside the material microstructure. In addition, the grains are elongated in a certain direction. What is going to happen after annealing? After the annealing, as you can see, for example, if we decided to observe this grain, for example, you can clearly see the grain boundary, it has a specific grain boundary, but it would be difficult to identify the grain boundaries of the other grains, especially this region in the middle here. But anyway, we could say that this is like one grain, right? And there is another grain somewhere, this is another grain, and so on. But in general, as you can see, the grains are not elongated anymore. That the elongation that we experienced after the Ecap processing, after annealing, we would have the grain boundary would migrate, and this would result in forming large grain sizes. So the grain average size will be generally increased due to recovery, recrystallization, and grain growth, because as we explained, annealing would allow for the 3 mechanisms to take place. So if there is recovery, definitely the dislocation density is going to decrease. If there is recrystallization, the contrast in the color between the grains should be relieved, and then somehow the lattice strain could be minimized and relieved. As you can see, there is white grains and there is very dark and black grains, but here almost all of them, they do have almost the same color, except a few grains like this one, for example. It has a different color. It is dark, that indicates that it still has some dislocations, and also this is dark. But the other ones, over all the other grains, they almost having the same contrast, but still they do have some dislocations, because these things, these dark things and colors indicate that there is a dislocation inside this grain. But this also indicates that the amount of the dislocation has been severely and significantly decreased. It means that definitely we moved to the recrystallization phase of the material microstructure during the annealing process. So we are expecting, depending on this figure, that there is recovery, there is recrystallization, there is grain growth. Why? Because the grain size, it is kind of became bigger, became equal axed, because of the grain growth and the migration of the grain boundary that would combine and result in large grains. In addition, these grains are kind of equal axed, they are not elongated anymore. In addition, the contrasts in the color indicate that we do have a relief in the lattice strain, we do have a decrease in the dislocation density up on annealing. So these are the changes over the material microstructure that we should expect based on these two figures. How about the changes over the mechanical properties of the material? What we should expect as changes over the mechanical properties. Before, pure titanium by itself, it is a weak material. Up on the Ecap processing and the severe plastic deformation, and we are performing this Ecap at certain temperature, let's say at room temperature. If we assume that this has been done at room temperature, so we are expecting an increase in the strength due to some strengthening mechanisms. This strengthening mechanism definitely it will be two, which are the strain hardening, since we are performing the plastic deformation at room temperature. The other mechanism is the grain size reduction. Due to the grain size reduction, there are more grain boundaries. As you can see, there are lots of grains here. The count of the grain is small in this case, and the size of the grain is bigger. But here we do have so many grains and so many grain boundaries that is going to work as impedances for the dislocation to move, indicating an increase in the strength of the material. So there are two strengthening mechanisms that they can explain why the strength of the titanium has been increased after 8 cycles of Ecap because of strain hardening and the grain size reduction. But there is no alloying here. We are still talking about the pure titanium, and there is no alloying process that is going to take place for this application. But what is going to happen? And also, what about the ductility? The ductility definitely is going to decrease because of the strain hardening, as we explained. But how about after the annealing? After the annealing, we are expecting recovery, we are expecting recrystallization and grain growth, and this would result in an enhancement in the ductility of the material, but in the meanwhile is going to slightly decrease the strength of the material. So after the annealing of this material sample, we are expecting a slight decrease in the strength of the material, but an enhancement somehow on the ductility because of the recovery, and somehow the recrystallization is going to take place up on the annealing based on this figure. So this is simply another example in how to understand the changes over the material microstructure and mechanical properties from the TM, and depending on the data that already provided, what should you expect as it changes over the microstructure and mechanical properties of this pure titanium, depending if it is processed by Ecap followed by annealing or without annealing. Make sense? Alright, so that's it for today. The objective of this video is just to give you like a comprehensive discussion about the different topics that we covered in this course, about the imperfections inside the material microstructure through chapter 5 and 4, also the dislocations, dislocation motion, the plastic deformation, the strengthening mechanism, the changes over the material properties for all of these different applications, and to understand or expect what are the changes over the material microstructure and mechanical properties depending on the material processing conditions. So here we are linking somehow the mechanical properties of the material to its microstructure, to its processing conditions. And these are the 4 disciplines. We said that we do have 4 disciplines of material science that we started in the beginning of this class. We do have material processing, we do have the material properties, we have the material microstructure or material structure. In addition, we have the material performance. We said that this material performance, this requires some practical application, like the use of this material for some mechanical application, like the mechanics of material class. You already studying the material performance, but the focus here is more on the relation between the material microstructure or the material structure and the material properties. Through this discussion, we connected the material microstructure to its properties, to its processing the condition. So depending on the material type, depending on the processing condition, we can expect what are the changes over the material microstructure and what are the changes over the mechanical properties of the material. This was the objective of this video. Alright, so that's it for today, and thank you so much for watching, and see you in another video.